Let's assume that equilibrium is established at the electrode-solution interface as a result of process with charged and uncharged particles. The change in the electrochemical free Gibbs energy for this system can be written in the form by analogy with the condition of chemical equilibrium. We obtain the equilibrium condition at the electrode-solution interface. The stoichiometric coefficients corresponding to the reaction products should have a positive sign, and those corresponding to the reactants, negative. For electrochemical potentials of charged particles, a superscript indicates the phase to which this component belongs. For uncharged particles, the electrochemical potential is equal to the chemical potential, and the indication of the phase is not necessary. Consider two simplest examples of the establishment of electrochemical equilibrium at the interface. First, the border of two different metals. When equilibrium is established at this boundary, the electrochemical potentials of electrons in metals are equalized. The equilibrium condition has the form or so, for the galvanic potential at the metal-metal interface, we obtain the expression Thus, under equilibrium conditions, the work of transferring an electron from one metal to another is zero, but the work of transferring a unit of an imaginary charge, that is, differs from zero, since the chemical potentials of the electron in different metals are not the same. Second example. Boundary of metal with the solutions containing ions of the same metal. When equilibrium is established, the electrochemical potentials of ions in the solution and in the crystal lattice of metals are equalized. In equilibrium, or so that the galvanic potential at the metal solution interface of the corresponding salts has the form insofar as the equation for the galvanic potential can be rewritten as an equation of a similar type, which instead of activity included the concentration of metal ions in a solution, was first obtained by Nernst. Therefore, this equation is a special case of the Nernst equation for a separate galvanic potential. Thus, under the conditions of the considered electrochemical equilibrium, the work of transferring an ion from a metal to a solution, or vice versa, is zero. The galvanic potential depends on the concentration of the potential determining ions and can also be reduced to zero. However, the impossibility of measuring the galvanic potential does not allow to establish at what concentration of ions the galvanic potential is zero.